אוקיי, אנחנו נתחיל. We'll start, I make the seminar in English. First I will introduce myself. ניתן קצת הקדמה על עצמי, ואז אני אעבור לאנגלית לשאר הסמינר. אני תום אגמי, אני סטודנט של פרופסור אלפרד ברוקשטיין, וביחד פרדי ודוקטור תומאס דג'ה גם הנחו אותי בפרויקט הזה. את התואר הראשון שלי עשיתי כאן בטכניון במדעי המחשב, זה התואר השני, ואני מגיע מרקע של 15 שנה בתעשייה של מכונות ורובוטיקה, אפליקציות של ויז'ן, וגם ניסיון ביחידה 81. And now we will go to the seminar. Today we'll talk, what is the hottest topic today? Iran, of course. מה הקשר של איראן לזעפרן? אוקיי? So, איראן, מגדלים את הזעפרן, אוקיי, איראן grow this flower for thousands of years. Okay? There is a big culture around this saffron flower. מגדלים אותו כבר הרבה שנים, and it's one of the one is, okay. The source of this flower, one of the big source for this flower, and we want to introduce you a system that can harvest this flower using a robotic arm and guided by a vision. What? Let's get some motivation to what we are doing here. Okay? To get 1 kilogram of saffron, we need tens of thousands of flowers. Okay, they should be picked. Today they picked like that, by handwork. Later, after they picked that, they need to sort it to different parts. What parts do we have here? We have the stigmata, the tzalakot. This is the part that we want to take. It's the most expensive part of the saffron flower. Also, there are stamen of kanin. עלי כותרת, the petals.
Don't translate it.
Okay, okay. We would like to pick this saffron flower in the perianth tube, exactly here. This is very important for the later process. We cover the harvesting process in this seminar, and later when we harvest the flower, we will transfer it to a different process for automatic sorting too. One of the problems they have that the saffron window time is very short, a few hours. You can't pick it too early, and you can't pick it too late. The quality degraded very, very fast. Okay, why this is hard? So first, in this image, the flower can be picked easily, no occluded, no obstacle, you just can take it. But why this is hard? This is the reality. We have leaves around the flower, it's occluded, we want to pick it there, exactly behind those leaves. And we can't see where we will harvest the flower. Also, we can't get it. Even we know exactly where to pick it, we can't go through the leaves. We damage the flower and the leaves and the plant. The next season also, it's need its leaves. So that's why we have here a challenge. Okay, I give you some motivation. Okay, and we will explain it soon. We will track the flower, we found it. Okay, and then we bring the flower to the robot, we serve it to it, and we pick it. Okay, now you want to know how we did it, yeah? So let's see how we did. Okay, our agenda for today's seminars. First, the system setup, static camera, rotating stage, and the robot. The pipeline, we make rotation, segmentation, point of interest detection, and then extraction. Then the vision algorithm. And we will show you some synthetic data evaluation and result that we can measure the vision quality, the gripper design, and the future work. Okay, first the system. We have a static calibrated camera here, and here in the top view. Simple camera, not stereo, not deep depth camera. It's simple camera from AliExpress. We have a rotating stage. You can see here from top view. And we will put the flower on this rotating stage. We can rotate the plant. And we have the robot that when I started the project, it was with 6 degrees of freedom, this robot. After I met Freddy, we degenerate this robot to only 6 degrees of freedom. We wanted to make all the process smarter and simple and cheap. And that's what we did in this project. We just used the 3 axes of the 3 direction, X, Y, and Z of the robot, and not all the axes that we have here. And later, after we estimate the 3D location, we can get the flower. Okay, here is a pipeline. We have here the flower should be growing indoor, not outside. In Israel, we have not a lot of land, and we want all the year to get this flower, not just one season. We have flowers that get on conveyor. Later, put it inside the rotating stage. Here's our seminar start. Then we rotate it, capture it all around. We make a vision algorithm how to detect the area, where is the interest points. Also, we use half, we'll see. And then we pick with the robot. Okay, this is the real flower. We want to pick it here. Okay, and this is the gripper. Later we'll see how the gripper also built. First, we need to do calibration. Here, our camera quite far from the flower. We're not moving the camera, and it's important to be accurate. We use a static calibration with standard chessboard calibration on the rotating stage, and then we use multiple views to make it more accurate. Okay, this is the calibration board. We put it on our rotating stage. You saw it here. We put this calibration board on this stage. Then we make chessboard that probably all of you familiar, which we know the points of the chessboard, and we make a calibration. One board is enough, but we will rotate it many times to get, even with low resolution camera and cheap one, the best calibration data specifically for the region that interests us, not the corner, not the distortion. We want exactly to calibrate it around the area that we need. We found the camera metrics and all those parameters. And our algorithm take into account that we have a circular movement in the plane of the plane. Then one flower is dragged while it's moving. And then we make optimization using half-style idea. After we detect the points, we make half-style to understand what is this curve and fit this curve first to the 3D. Okay, let's see one by one. First, this is not many flowers. This is only one flower that we assemble in one frame, made multiple times. In each of them, I show here the dot where the flower we want to pick it, the interest point. If you see, all the interest points make some ellipse curve in our image. In the reality, this is a circle, a full circle, but here in the image is an ellipse. And we want to estimate this curve in the 3D. Okay, so first we need to find those points. First, the interest point. For finding the points, we segment the flower. We segment it to three types of meanings. One is the flower itself, the red pixels, vs the leaves that become yellow, and then the background that is white. Okay, but it's not important just for notation. But we have three segmentation values. We want to get the lowest point, even if it's occluded. Okay, so to reach the lowest point, we first need to understand the plant. The plant can be grown not just straight to the sky, can be like that. We see it in reality. So we need to estimate the plant direction. We use the leaves. We found the leaves tips from the convex hull of the flower. We found the root. This is easy because we know that must be a root. The flower cannot be fly. And then we average all the direction with the purple line. We have the direction of the plant. So now we get the lowest point in our flower, but in this direction. Even we have a leaf flower pattern that go far away and it's lower to this axis, we look to this direction. We still want to take this point. This is from synthetic data too, okay, that we show the points that we want to take. Even we don't take exactly the one because it was occluded, it's okay. We will deal with this problem. This flower is rotated from different angles. Now we want to find the relationship between the 3D to the 2D, to the image plane. Okay, we know that in the world, our point that when we rotate it, it's form a circle with radius r and height h. This circle plane is parallel to the floor. But in the camera view, as you can see there, when we rotate it, it's become exactly ellipse. Now we want to understand the relationship between this ellipse to this the real circle in the world, because this is the 3D dimension that we work, and this is the image plane. Okay? So what we found at the end of the day, if we have time after the presentation, we can delve into the mathematics, but we found the relationship between R and H. We have a ray from the camera center through a UV coordinate in the image plane. This ray, exactly because we know where is the camera, the direction, and all the parameters, we know exactly where is this ray in the 3D world. And if you just Gini Welder and gave us H, we could know R exactly. But unfortunately, we don't know H. We found the relationship between R and H as a function. Okay, R given H is a quadratic square root of quadratic function, where A, B, and C, those parameters, can be calculated from the constant K, the camera matrix, and T, translation, and the R rotation of the camera, and UV coordinate that explain us where the ray is points to. From these parameters, we have a constant A, B, and C. And H is our function. It's our dependent H. That's what we found. And how this curve look, and we will first, we will take this curve for each point, and we will use the half idea to find the intersection of all these curves. Half voting. Okay, instead of line and polar transformation, we use our R and H parameter space. We make a voting in the physical meaningful R and H space, and each point contribute a curve in our space, R and H space, and the intersection indicates consensus between all the functions together, or not necessarily all, but we will take the one with the highest consensus. Later, we do a small post-processing on the accumulator matrix of the half. I don't know if everyone knows about half background. So later I show a small example that explains it too. But each function square root of quadratic formula apply this curve. Okay, this curve is belonging to one point, and this for another point. All these curves intersect in one point that where R is the y-axis in this diagram, if you can see, and H is the x-axis. Okay, so we know that this point is R is 60, and H is about 120. Okay, then we know where is this circle from the half idea. Let's see the half idea. Here I do a simple example with less curves. Each point represents a function in the half space. And together they are intersect in one point. I have a video that shows which curve belonging to which part of the ellipse also. Okay? Each time I click on the ellipse, this is not, I don't know the ellipse, we just now try to estimate it, and then we draw. And especially I put outside some points. It's okay, I do some outliers. And while we move on, now we get the upper part of the ellipse. It's go to the second side of this butterfly. And all of them intersect in one point. You see R is 59, H 99, here R is 60, and H is 100. It's very close to our real ellipse. And then I put some more outliers. Very noisy outliers. Still, our R and H quite acute. This is what we want, because we don't want optimization that stray from the real values because many outliers. And we have a lot of outliers that show us that the consensus is here. And we are very close to what we want. Okay, later we can make histogram of R, which R is support. This is now R is the x-axis, R60 support the most of volts. It's mean most of the, if we take all the height, most of the points vote that R60 is acceptable in the function. And there is the accumulator vector that this is the dense area, a lot of intersections, very close to one each other. And we want to get to this. In this area, we will form a small post-processing to get better R and H. And we have some logic for that too. Okay, we want to find height support radius beams. And then we collect some candidate in this area. We don't just take the maximum one. We take the candidate in the dense area where a lot of consensuses are there, and we prefer the lower height. Why we prefer the lower height? We have a little bias because the occlusion. Each time we have occlusion of leaves, we take upper point. The point that we take is a little bit more up than the target one, the real one. So we have a bias because this system, and we prefer a little bit. We don't do a larger correction there, about 2-3 millimeters, and also our accuracy is about 5 millimeters. This is good enough to catch the flower. 5 millimeters is משבצת חשבון. There is quite small, and we reach that accuracy. That is the post-processing to choose a better R and H candidate. Here is a sanity check. We put a point, and we use our calibration matrices, and we reproject the fitted ellipse after the half process. This is not from OpenCV ellipse. It is from the half process reprojecting to the screen. We wanted to see that we are making a nice fit to those points. Now, after we found this place, it's not enough. We have a place, 1D geometry place. This is our ellipse, this is our circle, but we don't know where to take it. Also, as we saw in the start, we can't go directly to this point. Even we know exactly on the circle where is the flower, we can search for the closest point, for example, on the known circle. We still can't go directly to take it. And we don't want to guide the robot to use more axes to get this point. So what we are doing here, we know from the half process, we took a lot of interest points, and we know there that of each point we can calculate what was the theta of the point. Theta 0 is exactly the plane of the calibration board toward the robot. Okay, so we know exactly for each point that we segment before, it's roughly the theta that it was around the rotating stage axis for each point. Now, pi is a point from previous. We have maybe 100 points from previously. We take the point and we search. Okay, let's see what is C of theta. I need to explain it. C3D is just R sinus theta, R cosinus theta, and H. This is the 3D position of a single point. You just give me the theta and R and H that we are estimated. I can tell you exactly where is it in the world already. C, small c of theta is the projected of those of this point into the image plane. So we project it back to the image plane, and then in the image plane we can find a close enough point, and even exactly on the ellipse. So from around plus minus 20 degrees to the robot, we want to take the minimum one. That we know why we take a small distance position between the point on the ellipse to the point of the flower, because where this distance is 0, exactly on the ellipse, we know that there is no occlusion, that we have a ray that we can see directly the point that we want. Instead, this is a very nice idea that instead of calculate all the obstacle, we know exactly where is the leaves. Instead, and make algorithm for planning, we just know that there is a direction, that we have a straight movement toward the point without touching any leaves. And now we found the flower roughly, because maybe it was occluded, so it's not exactly, and we will bring it to the theta base that we found, that we know that this position is good, no occlusion in this position. And this was P and T minus 1, the last image that where the flower stopped. We just rotate it. We don't know where we stopped. It can be here, it can be here. We stopped it, we searched where it was, and then we rotate it to the point that we know that there is a ray to the point. It's good for the robot. And then we recalculate it again to make it secure enough. It's important, and then we can take this point in a simple way. Okay. Now we want to talk about the end effector. We don't just use a big gripper that catch all the leaves together. It will not work in this situation. We have a small environment. And we want to use our 3D position and to guide the end effector without interference with the other leaves too much. It should be very, very narrow, and you will see it now. And we want to make a simple motion planning. We do not like to use too much axis, and we want to make it simple. So this is our gripper. What you see here, a catch and cut mechanism. This section is a top section view of the flower. So above this stem, we have the flower. We cut this to see the mechanism. The gripper will go toward the stem, and the stem get into the slot, and then we catch and cut it at the same time, like that. Whoop. We remove a little bit the stem. Let's see it again. Opa. Like this, and then we catch and cut it. This is the idea of the gripper. We use the flexibility of the flower, then we can widen our tolerance of the accuracy, and also have a tiny gripper that's good for this process. This is the real gripper. It's like arrow type, and here is the slot that we will go below the flower. Here is a side view. The stem will slide here and get into this slot. Okay, and now we will show you a little bit experimental evaluation on the vision process. So to measure our vision, we had to have a ground truth. Ground truth in real plants is hard to get, so we did a synthetic data set that we know exactly R and H in each plant for each flower, and we stratify difficulty in a three level of difficulty. Okay, plant with one flower, plant with two, and plant with three flowers. Because one plant can have up to 3 flowers. More than 3 flowers is very not common. And then we want to see our error in millimeter level, to see that we are in the area that we need for this project. Okay, so here is one plant, one flower per plant. One ellipse is the ground truth, and the second one is the estimated. And here we have it two for 2 flowers, and another one for the 3 as well. So our metric is the Euclidean distance in the 3D space. We have delta R, is the distance between the small radius, the ground truth or the estimated one, to the second ellipse, and delta H, the difference in height that was estimated from the algorithm, and we take the Euclidean distance. This is our metric. And what we see here, the blue points represent plant with 1 flowers. We did 20 examples from each category, not just 1, 20 samples to get some probability. And for the blue points represent 1 flower. We can see that the radius was quite well estimated, less than 0.5 millimeter. That it's really great. The height is 2.5 millimeter, the average 3. It's still good. We have until 5 millimeter, we are very fine. For two flowers per plant, it's a little bit wider, but still it is good. And for 3 flowers, we get it even worsened. But still we are fine to get in 3 flowers our results. So this shows us a little bit the scatter of the points of the errors while we make the scene more challenging. Here, we want to understand how many frames do we need to get enough accurate results. Because 1 or 2 frames may be not enough. That's why the stereo camera at the beginning of the project was failed, because stereo also get occlusions and those things. So for 10 frames, we take what we did here. We took 120 frames. Okay, now we did a downsampling, and we sampled just 10 uniform frames, 20, 60, and 120. But we see that in 10 frames, when we have 3 flowers per plant, our error can be very big. 15 millimeter, it's too much. Remember that we need 5. But when we get to 20 frames, we have, in all the category, we have the error is enough good for us. And if we continue to 60, it's even lower. Okay, so our error then, and to 120, we didn't get almost any improvement. It means that even 60. Why we care about the number of frames? Because we use a simple camera, 30 frames per second. If we want to speed up our system to make the rotation in a faster time, that means that we get less frames. Our algorithm is real time, so the frames depend on the camera. There is no we don't delay the camera determines our speed. So in 60, it's 2 seconds for rotation, and it's very good. We have until 4-5 seconds, and even 120 we can reach. Maybe in future work, we try to challenge the 60 and go to 1 second and do crazy things. But now we are here and we are very fine. We are far away from the place that we have not enough frames.
So rotation is 2 seconds usually?
The rotation, now I did 120, I did 4 seconds. And we have this time for this pilot was accepted until 5 seconds. And we are there. But we want in the future to get to 2 seconds per flower, so to make it more interesting, more faster. It's always better. So that's why we make this measurement to see if we have a problem. This is example of we have 2 flowers. Both of them were detected in our algorithm, depend on where it's been in the rotation. Okay, so each one of them make us in the half plane many functions, and as you can see, there is 2 groups of functions, one for each of the flower. That's why we have here 2 butterflies or two structure, and we have 2 peaks in the histogram. That means that we potentially take these peaks, but we do it in a more safe way. When we want to pick a flower, we take the flower that we see the most of the times, we pick it, and then we do it again. For this time, it is okay, and it's fine. What's the problem with 3 flowers? You can see here that you call it stealing points. This is the problem. Okay, all those points that not on the ellipse, the red points, belonging to a different flower. While we rotate the flower, another flower take us give our algorithm the idea that this is the candidate for bee picking because it's the lower one, it's the most seen one, you can see it better. So there was in the circle a place that another flower took this point. We lose it. That's why also intuition, we had higher errors when we moved to 3 flowers, because they steal our points. Here is another example, 2 plants. Okay, that especially we had a big area because we do 2 plants. It's not our project, it's just a test that I try to see my algorithm or our algorithm, sorry. We have here a big area of outliers because it was occluded very much. This flower occluded this one in a specific area, and a lot of points were outside of the circle, and still our ellipse estimated was quite good. Even we have, I don't know, maybe 30-40% of the points was not correct, and even not belonging to the second one. But still we get nice estimation here. Now we talk about the limitation and assumption. Our assumption that our stage is fixed over time, and we know the axis of the rotating stage, and the camera calibrated and fixed over time. It's not moving, and it's okay in our environment. The flower is approximately circular locus. What this assumption means, that it's not trivial assumption, but it's from the experiments that we did. This assumption means that while you rotate the flower, it will not vibrate, it will not, the centrifugal power take it away, and you get a different circle, and when you stop it, it's moved. So this assumption been checked, and we see that it's okay, but it's one of the assumptions here. The segmentation also yields for enough correct points. This is our assumption, and it depends on the frame rate and the time that we make the spin and the occlusions. And what can make failure to our model is mixed points from neighboring flower, the stealing point problem, and also occlusions. Severe occlusions that bias our height a little bit, and then it's risk our position. We wanted a Q position in the period tube, sparse angular coverage, a few frames, we talked about it, and calibration drift. And this calibration, that's why we improve the calibration to have the rotating axis of the calibration board, to get it more accurate, even the camera quite simple and the resolution not so high. In the summary, we did this project with static camera, rotating stage, and we get a cheap multi-view geometry. The half voting gave us high stabilization and robust way to detect the curve. And now we did ellipse projection again. And we search in the 1D, because what it means, again, the circle take our 3D world to a 1D world. We just need to know where is on the circle. Quantitative results show us that we are fine in the accuracy that we want, millimeter, and then the factor help us to make a straight line movement without too much calculation, make it simple and cheap. Here is again, now you can understand this video. We rotate it, searching the base of the flower. Okay, we make the half optimization. We bring the flower to the robot to a position that it can take without touching the other leaves. And it can take it. The second one was with a different gripper for two flowers, without the catch mechanism that we start at the beginning. And then we found the flower, and we get exactly into the flower. Okay, it was before, we take it out, and because it don't catch, it can fall, but it's okay. It was, yeah, Sheila?
And so you make the assumption that the flower is rotated, and you rotate it until you find the optimal point?
No. My assumption is I'm not rotating until I found the point. I do the rotation, full cycle rotation exactly. I don't know where is the beginning point, just put flower and rotate it. Then I search where was the curve, the nice position in the 3D world. I search where is it roughly on the circle, and I bring it to a point that I know there is no occlusion there. So I don't now search again while I'm moving. I exactly move to this point. I can move even faster. Let's see again. Okay. I do now the rotation. You see the flower starts roughly here, and it will stop roughly here. Okay. It stopped here, not more than 1 0. And make a small pitch because it was accidentally close to the robot. Now the second one is far from the robot. It will do another rotation because I want a new point. We have enough occlusion here. I stop it here where it starts, but it is not good position. Then I take it directly to the position that I know that I have a free ray to the flower.
Okay, but if you were to apply to a real world setting, say field, so assume your robot is
In the field, you mean?
Yeah.
Okay.
Yeah.
So this project is a good
the
question.
robot would do the encircling values.
In the field, it's different story. And it's a good question because this project was for indoor growing, and assume that we have flowers that moving on the conveyors, as I saw in the pipeline. We don't go with the robots and the camera to the field, to the boats, the mud there, and then, no, we do it in this way, and then we have controllable environment. The camera is fixed, the calibration is good. That's why we can assume a lot of good things that make our system so cheap and easy. Okay, here is the different levels that we tried. We tried first without any occlusion. Just to show you sanity check, we put flower with no occlusions. The camera looks from there, quite far from the flower. We rotate it and it will bring, it's because no occlusion, straight to the robot, even not roughly, because it takes the best point for the robot, no occlusions. The second one is this same flower but with occlusion. Okay, and we want to see that the robot know to bring it to a position that the occlusions will not take care, not make problems, and not be an obstacle. And here another flower with our old type gripper that will take, okay, from here, it's easy to take, you see? From this direction is bad to take, and it will bring it to this area. It will rotate it, and then it take the flower too. Now another question. Yes?
Did you try to generalize the approach to other paths rather than circle?
What?
Not just, I mean, you rotate it, but you can have it's relative rather than the table is circular, rotating, then the robot will move around in other path rather than the circle.
Maybe, yeah.
Okay, you mean the camera on the robot? That the camera is moving. We consider at the beginning to move the camera, and we talked about put a simple camera on the robot arm. That is more traditional way to make picking. And we saw that because if we make a good calibration and good assumption and good algorithm, we don't have to. It's now the robot go without seeing nothing. It just go to the point and it works. So אם זה השאלה? או לא?
כן, הכוונה היא בעצם להשתמש בזה בגרינהאוס או something.
You mean about moving to move the
robot inside the greenhouse. You want to have a robot that is moving and then
that the robot will do the movement instead of the plants.
Yeah.
We consider it, we talked about the rotating of the camera, not moving with the robot. You mean driving in the field, like they do for tomato, for example. I don't know if they succeed already.
That would have to be in the field, so it could be greenhouse or something like
In
this.
the greenhouse.
Because it's more realistic. It doesn't require
It's a good option. We didn't do that. If you ask if we did, we didn't. We had some idea. It's possible to move the camera. It should be equivalent to move the plant if we know the trajectory. We need to know the trajectory. We can fit our algorithm to a different curves. That's a good point. You can fit it to a different curves too. But not all the curves. We need to see also the R&H was quite long way to get this relationship.
No, but you can do it with a linear
motion.
Yeah.
We can have some options. Great point. Thank you. Okay, more question.
Yeah, I have some questions. Did you have access to some real flowers at some point?
We had we had the access, but not for picking them. It was for capture them. And what I saw in the presentation, not this, right? Some of the flowers here, we did the vision and the segmentation. Okay, this was a real flower. The segmentation was real. It was, we did the segmentation without the segment anything model or like that. We did the real-time segmentation simple by using the environment light and our assumption. So we did it for the vision test. You are right that picking, we need to get those examples. It was hard to get them, and the window time that the flower is live, very short, the blooming time.
Yeah. So something that I'm worried about, I mean, you know this, is that when you rotate the flower, you will have some vibration because in your synthetic experiments, they're like pieces of metal, whereas the real flower will be a bit more flexible, maybe.
But we did rotation. Wait. You make our circular assumption, yeah?
Yeah.
But why, when we rotate these flowers, we rotate it,
This is a real flower or it's a synthetic?
it is not a real, but it's a real, not synthetic one. We build these flowers with the same size of the real flowers. We have the same size.
Yeah, but the green thing is a plant or is plastic or metal? What is it?
It is
The rigidity
of the physics of the flower.
It's a good question. This is good for our future work to check this.
So about this, my suggestion is that you showed that you only need 20 pictures, right? Uniformly, and you get good precision for your estimates. So all you need to do is buy 20 cheap cameras from Alibaba, put them in a circle, and then you don't need to rotate your plants anymore. You just take 20 cameras, take a picture from each camera, and then that's it. You're done. It's as if you've rotated everything.
Cameras, yeah, it's okay. I think it's cheaper. One camera also from AliExpress.
Yeah, the trade-off.
It's possible, yeah. You're right about a lot of camera, but not easy to calibrate many camera. But okay, your suggestion.
It's an option.
It's an option, yeah.
Yeah.
Yes. And you can see that the leaves at the end, the tip of the leaves moving while it rotates. It is moving. You can see that the leaf is little vibrate. So it's quite thin, but his point is right. Yeah.
Also, why is there a bias in your estimates? Can you go back to the scatter curve?
Again?
Scatter plot.
The scatter plot
Of
of the three types.
Yeah.
This one. And you see, like the one flower, there's a bias. It's always positive, right? The delta R. Like you're overestimating the radius or something. Why?
Yeah, a little bit.
Yeah, I prefer to take lower point instead of touching the flower and making the picking. It's okay to go a little bit down. It's fine for our.
But this is the radius. It's not the height, right? So the height, it's okay. It's negative. So you see your heights are all in the negative space. So you don't cut the flower itself. You cut a little bit lower. But the radius, like, why is it overestimated? It should be centered, no?
What do you mean overestimated?
It's always bigger than
maybe
bigger than zero.
I think that because the flower is not a point, it's thick. There is a thickness of the stem, so we get 1 millimeter, maybe a little bit biased there. I didn't delve into exactly the ambiguity of the area of the stem because we get a great results already that was fine for us. So in the radius, what we take in the dense graph, in the half, we take the average one, that's it. And the average gave us this millimeter. Also, in our half plane, we don't use precisely half too much because we need to have accumulator vector. So also we use half millimeter scales or something of the grid size.
But the cutter gives you a large tolerance, the cutter itself.
The cutter that we use, the flexibility of the camera, of the plant, sorry, of the stem, and the slot give us a nice tolerance to deal with the radius, not with the H, but with the radius. With the H, we prefer a little bit lower. It's fine to the next process of the sorting. Okay, more question?
The question that comes to mind is where have you used AI in this, and whether you have used AI at all in the project, and why not do everything by AI? Do you do the classical?
It's a great question, and
computer vision thing.
It's great question, and
Why don't you just train on a million flowers?
So first, the deep learning, one of the problems is that we need a lot of data set, and if we need the reality flowers, we need a lot of reality flowers. Even the models that we did a few models, we need to do maybe thousands or hundreds of it. Secondly, the deep learning disadvantage is real-time applications. Here, I use it's real time. I wait to the camera, not the camera waiting to the algorithm. I also, while I do this algorithm, I have all those process videos. So I capture the video, I process it, I put points, I segment it, I do all the things, and I'm still waiting to the camera. And in Python language, even not in C. So the idea that use simple tools give us a good opportunity to deal with fast movements and these things, and not need to train a lot. But I did a small
segmentation.
The segmentation, I did a small model, small CNN, but very local CNN based on colors and the pixel and the structure, 3-on-3 kernel. It was very, very small, very small and tiny, that can be trained just by the points itself. I say, this is flower, this is flower, this is many times. This is point of flower, this area of its leaves, this area of background, and I trained it in about 10 minutes without the necessity to go to wider data set. זו השאלה? עוד אחד? Okay, yes.
If you increase the velocity, the rotation velocity, so is still your assumption that there will be no rotation or no movement of the plant during the rotation?
It's a good question. Our circular assumption, and that's what also Thomas say about flower. That's also there are many types of flowers. In the first year they are quite short, and later they become tall, and all the leaves can be vibrated. But the convex hull or the wall direction of the flower should be estimated quite nice, as we think. But I don't know to tell you if it will do. I tried 2 seconds spinning, and it was okay in our flowers. But in a different scenario, I need to check it. Maybe we need to rotate lower. Maybe also, if we know the height, and maybe there is a formula for the centrifugal power that we can find to correct it. It maybe depend on the height, we can correct it later. We can do things when it will be the time. We will do.
If you can.
There are a lot of ideas that could be tried when lots of flowers are available, but in the meantime, the growers are having trouble growing the flowers. And
it's not easy. It's not easy. There are some startups in Israel that try to grow this flower and to make it a lot of seasons, and it's really hard. one of them succeed a few times a year, one of them was not succeed. They are learning about the lighting and the environment. It's not so simple. It's process, but for different kind of
They are
people.
in the deep learning process of how to build the
Yeah.
It's very interesting research. And,
Thank you.
we're looking for.
I would like to ask
Yeah.
if you would rotate the camera, it was the same. You could use this.
It's a good question, and also one of the people in the audience asked something close to it before about moving the camera in a known way. So in a circular manner, I think that it will be great. Maybe the same, and then all the problems with the vibration and the winds will be disappear in 1 second. And maybe yes, it's maybe a good solution to rotate the camera instead the flower, make it robust and accurate enough.
What Thomas say about the many cameras, you just can put it on a round chishuk, yes, on a ring.
On a ring.
On a ring,
On a ring, yes.
Yeah.
And put the camera on the ring and let it.
It is great, yes, and then it solves many questions here.
Yes.
It's a good suggestion. Yes.
Yeah, but you still have to take from many images. You still have to decide where is the picking point. Yeah, it's the same.
I think the algorithm should be very similar, but I think it's a great idea. Yes, I will put it in my mind.
Yeah.
Remember that if you move the camera, you'll have motion blur. So if you have several cameras that are fixed, there's no motion blur at all. That's the idea.
But also you can say when I rotate the plant, I have motion blur.
Exactly. But if you don't rotate anything, there's no motion blur. So don't rotate the plant. You get 20 cameras, don't rotate them, and you're done, right?
Cameras.
It's a good point. We need to see. I didn't do this test yet. When we try, when we see if we have the problem and we decide to switch, you will welcome to my next seminar.
Well, in the real deployment, also the robot will be much simpler than this robot.
Yes. This robot
we are going to build a robot that is not downgrading of 6 degrees of freedom robot, but it will be like a very simple two motor.
Yes, that's a great point. This robot that we did generate to 3 axis will not stay, of course. We want to make it very cheap with the less of axis that we need. And very small, of course, for this small flower, we don't need the structure of this robot. We want to make it smarter for real industry, for real use, and not just a pilot.
Yes, and cameras are cheap, so we can put
cameras all
over. Yeah.
It's already cheap. It's a computer camera here, and this is also camera less than $75, no tax.
One card is more expensive than the camera.
They raised it to 150, by the way.
Oh, so we can move to 2 cameras.
How much is the camera?
I don't remember. It's tens of dollars or something like that. Not too much. But as she said, now they increased the custom to 150. We can buy 2.
Okay.
Okay, more questions?
Yeah. Some more questions, some suggestions.
Talk about the movement of the camera, the movement of the robot, whether it's an arm or an axial one. But isn't there supposed to be some hand-eye calibration between the picker and the camera itself?
It's a good thing. Yeah, about between the robot to the stage. Yeah, there is hand-eye
calibration between the camera to the stage, so it's same thing.
Yeah, we have from the camera to the stage. Now we can do from the robot to the stage too. And what I did, I put the calibration board here, and I brought the robot in a vertical way as we used, and put it, and I put it here, telling this is the point now. Go to here, this is the point now, and I did simple calibration. I didn't do it automatically, and this robot have you're right that if we switch to a simple robot, we need maybe to care about the calibration more. This robot has absolute position. When you turn off power and turn on, it will remember the location, but maybe in the future we don't have this, and we need to do the calibration smartly. Good point. Thank you.
And actually, what we should start thinking about other problems that might be handled by such an approach. Not saffron flowers, but some other flowers, some other objects to do all kinds of things. So it's like a cute example of vision and robot coordination that could have many other applications.
Okay, so first I want to thank everyone that you come to my seminar. And I really want to thank for Professor Alfred Bruckstein and Dr. Thomas Teje for helping me a lot.
Actually, we thank you for a real application that doesn't involve deep learning.
Involves the real AI, right? The half transform.
Thank you very much.
Thank you.
Thank you.
Thank you.
So, ideas. Okay, good.